happened? Okay, so I said that I wanted to do a quiz grade today on 7.1, right? So if you have 7.1's homework that I asked you to have prepared, take it out. And then what I'd like for you to do, take out your notes, but put your book away. So just your notes, your formula sheets if you have them. Just no book. You can use your homework. All right. So what I have here is a little quiz. So we'll do 2 quiz grades today. I want to see what you can do on your own with this. Okay, so not working together. Everyone okay with that? Understand? See how you do with this. Please take one and pass it back, please. Here you are, sir. So we're not going to take a whole lot of time because really the quiz grade, the quiz that I just handed out to you, I really just want to make sure everyone does number 1, okay? If you do number 2, number 3, I'll consider that to be like bonus on this, all right? On this quiz I just handed you. So I'm not going to give you like 20 minutes to work on this. So it says use the provided image to find the following. And I say just set up the integrals, do not evaluate. So the first thing you want to do is find the area of the shaded region. And then from there, find the volume if you rotate around the x-axis. Then there's one on the back. Find the volume if you rotate around y equals -2. Right? Here's the image. I'm about to pass that out. All right? So everybody take an image. Go ahead. You can use your homework and your notes on that. There might be an extra in there. Here you are. Everyone have one? Okay. We'll give you seven minutes to at least do that first one, right? Everything else is just fluff on top. We're doing this quiz. You're allowed to use your notes and homework. I want you to at least do number 1. Number 2 and 3 is just bonus if you get to it. You only have 6 minutes left. All right, so the quiz, the picture that we had looks something like this. Okay, told you that this was y equals 5 minus x squared. This one up here was y equals x squared minus 2x plus 1. All right, so depending on how you went about this, you might have first went and tried to get your limits of integration, or you might have just tried to come up with the formula with the rectangle first. So it just depends on you. We're trying, of course, to get this area in here. So I think this problem is perfectly suited for a vertical rectangle, which means that our integral will be with respect to x, because our reference rectangle is vertical. If I go over here to the side, actually I don't like the way I drew that one. Let me draw one that's maybe over here instead. So if I look at this right here, got my rectangle like that, got the red function coming in on the bottom, got the blue function coming in on the top like this, right? So the area, I want to know the area of that little piece. The width of that piece is dx, so I need the height of it. The height, let's see, this top is what? How high is that? That's the 5 minus the x squared. And then this one right here is x squared minus 2x plus 1. So the height of just the rectangle is the 5 minus x squared, take away the x squared minus x squared plus 1. So this is the f minus g in the integral, right? So our integral will go the f function, the top one, 5 minus x squared, minus the bottom function, which is x squared minus 2x plus 1, and then dx. I'm going to put the whole thing in a big set of parentheses like that. So now for the limits of integration. Okay, the limits of integration, you have to actually find where these two curves intersect. And I would expect on a test for you to show that to me algebraically by hand, all right? So you would need to be able to show the intersection. What is that? Negative 1 and 2. Okay, so how do we get that? Set them to each other. And then solve this equation. Well, it's a quadratic equation, right? So we move everything to one side. So I'll add x squared to this side, which gives me a 2x squared. I already had a negative 2x. I subtract 5 on both sides. I get minus 4 equals 0. I can pull a 2 out of everything and dump it, right? Or divide everything by 2. And then I can factor this or use quadratic formula, although the quadratic formula would take you a while. And hopefully everyone here can factor this. And then you get two solutions, 2 and negative 1. So we should hit when x is 2 and negative 1. And you can kind of tell from the picture, or at least the picture I gave you was accurate because I graphed it properly with the software and then I pulled all the labels out. So you couldn't tell where things were. But yeah, negative 1 and positive 2. So negative 1 to positive 2. That's what I was looking for right there. Okay? If you didn't get the limits of integration, of course, it's going to cost you. But if you at least got the integral set up properly, that gives you something. Well, yeah, for the test, definitely. For the quiz, let's just say this will be a get out of jail free card day. Yeah, I saw you using it, which is fine to check your work. I mean, I have no problem with that. But we don't want to rely on our calculator to solve equations like this because that's kind of the idea here is to use what we know already to do it. You know, I don't know. We're getting back to that debate again. How much technology do we want to integrate? Because you can type this integral in to the TI-89 anyway and get the answer. So, okay. So there's a bigger moral of the story here, though. Coming into calculus or into Cal 1 or Cal 2, there's certain equations that a student is expected to be able to solve. You know, linear equations you should be able to solve, quadratic equations you should be able to solve, rational equations with fractions where x is in the bottom, radical equations, logarithmic equations, exponential equations. All those equations are fair game in a course like this. So if your functions turn out to be maybe an exponential function, two exponential functions, you're trying to find area, you might get an exponential, when you set them equal to each other, you might have an exponential equation here. The expectation is that you can solve that. So just because everything I've shown you has turned out to be linear equations or quadratic equations, just be aware that, you know, it could be a radical equation where you have a square root of something equals something you square both sides, or whatever the technique is. I just don't want people to be blindsided by something like that. All right? Okay. That's for the area. You want to know the volume, right? So for the volume, the only difference, I mean, it's the same picture, isn't it? We're going to rotate it around the x-axis. If we're going to do the x-axis, it's that same picture. So I'll go ahead and do it on a new page. We have our axis of rotation is here, which just happens to be the x-axis. We have our rectangle. I'm not going to put the y in there. I'm going to kind of exaggerate it. I don't remember. Was it blue and red like that, or the other way? Blue on top. So the only difference here, you know, our height is still the 5 minus x squared, and the height here is still the x squared minus 2x plus 1. But when we rotate that, the formula changes, right? That's all that changes, really. We're going to have pi. We're going to have integral. It's still going to go from -1 to 2, so that doesn't change. But instead of f minus g, it's f squared minus g squared. So all you have to do is the f squared and then the g squared dx. That's it. That's if we go about the x-axis. Now, if we go about the line y equals, what was it, -1? Or was it -2? Y equals -2. So the difference in this picture is that if we have our x-axis here, we have our rectangle, we have the blue on top, the red on the bottom, so that's all the same. But now we're going to go down 2 units for our axis of rotation, right? Y equals -2 is a horizontal line. So our axis of rotation down here, y equals -2, means that if I'm trying to find the distance from the top edge of that rectangle all the way to my axis of rotation, which we call like the outer radius, it's going to be the height of that function, which goes from here to here. That's 5 minus x squared. But I'll always have to add this amount. And this amount is fixed at 2. So I will have to add 2 to this. Not -2, right? +2, because it's a distance. So that'll be that one. And then the inner one, the inner radius from here to here is the, well, we knew from here to here was x squared minus 2x plus 1. And then again, this distance from here to here is 2. So what happens when I put this together? I add those. What do I get? 7 minus x squared. That's the outer function, 7 minus x squared. So in my integral, same thing, pi goes out here, -1 to 2. But the outer one is 7 minus x squared, and then I square it. And then minus this one right here, when I add these together, I get x squared minus 2x plus 3. Then, again, squared, and then dx. Understand? Another? Mm-hmm. Well, it would have to be linear. If we have an axis of rotation, then that rotation axis is going to need to be linear. Now, everything we've done in this class has been either horizontal or vertical. There is a way that you can rotate a region around a line that's neither horizontal nor vertical, so just an arbitrary line, but it's beyond the scope of this class. It's a little more involved. There are methods of doing it, yeah. We don't ever cover it in here. In fact, I don't think the book even mentions it. There are some calculus books that do it. I've seen it, but not many of them do. That, when I say textbooks that are used in a lot of universities and stuff, don't have that. Okay. All right. So last class we were doing these volumes, right? We were rotating, and everything I did I drew by hand. But there's a couple of cool demonstrations out there on Wolfram's website. Did I ever show you that if you go to like Google and type in like Wolfram demonstrations, they have this thing called Demonstrations Project? And basically what it is it's Mathematica, which is the program that that I told you I have that I use for my animations. It's people out there that are using Mathematica, that are coding things up, and they're sharing it with other people. So it's like a database of projects that people have put together. And you can search just about anything here. There's a lot of really cool stuff here. So if I just type in solids of revolution, then I'll find all sorts of different things that people have submitted. Now, I've written my own codes for this, and I can show you mine. But what's happening now is that textbook publishers that have a lot of money, right, because these books are expensive, what they're realizing is that everyone's going to ebooks. And so within the ebook, they're having these links where you can click on them, and it'll open up like a demonstration project in Mathematica. So like Mathematica is really becoming the standard that's being used for these visualizations. So the publisher is actually paying people to code up stuff. So someone's getting paid to put together a nice little thing here, and then that's incorporated into the ebook. So as much as I like coding and I enjoy it, I'm not getting paid. And you know what I'm saying? I'm not getting paid to code, and these people are like professional coders. So their stuff is really, really nice. So instead of showing you my stuff, which kind of sucks because I like this stuff. Like this is mine, okay? This is the one I did. It looks kind of cheesy now, but it's just the basic idea of you have a function. We're trying to find the volume of it if you rotate this, right? So if you take just a rectangle like we've done before, this is three-dimensional. You see this? And then if you can move where you want that rectangle to be, all right? And you can change the size of the rectangle. And then you imagine just rotating that rectangle around the x-axis, and you get this kind of disky looking thing. But you can see there's some problems with my code because I just have it draw a bunch of rectangles. I mean, a bunch of, yeah, rectangles. So there's gaps in between here, right? And then if you do all of those right, you get your solid of revolution, which looks like this, right? Looks like a football, basically. Okay, so that's my code. Now, my code's not too elaborate here. But now let's take a look at somebody who's done this professionally. Now, if you own Mathematica, you can actually open up their code in the document. So you can open up their code and take a look at their code. And anyway, so this is theirs. So here we have a region in two-dimensional space, right? We have an upper function, right? And then we have a lower function. And look at our axis of rotation is down here. See that? So they even like adjusted the axis of rotation. We're going to take that and we're going to swing it around. When we do that, we get this over here. Whoa. Let me pull that thing over here. And okay, I'm going to take the axes out and I'm going to not make it translucent. And then now you can really see what the solid looks like, right? Right, so that's what we're doing. We're finding these volumes of solids of revolution, right? The method that we're using here is what they call the method of discs or washers, right? We said that each time we took a rectangle and we rotated it around, we got a washer because it had a hollow center. If you don't have a hollow center, then it's a disc. So we call this the disc or washer method when you do it this way. And that's what we learned, right? That's all we've talked about is this disc method or washer method. Now we can also rotate around the y-axis, correct? Or vertical lines. Now this demonstration doesn't have that, but you could. So they also have a different region. You can switch it and have a different graph over here. Then you try and say, oh, you know, what is that going to look like? You know, if I take that and pull this over here. If I take that and rotate it around the x, or not the x-axis, around this line, like what does it look like? Well, were you thinking something like this? Does it have, see how it's hollow there? In the center, right? Because you have a little bit of a gap here. So on one side, you'd barely be able to get your fingers in there. On the other side, you put your hand in, right? So you can really see it with that visualization. So cool stuff. I think, you know, technology can really help out with the visual part of this. Okay, we talked about that last class. We're okay with this? Understand the setup on things? All right, now the other thing we talked about was what if you have like an object where you put it on the ground, and on the ground it's the intersection of two functions, then above it it's rectangles or squares or triangles or circles. Remember that? Yes? Okay. I have my code for that, which about a year ago was pretty damn good code, but now it's not so much. So this is my code for this. And so look, oh, wow. I thought I could take those little grids out. Let's see if this makes sense to you. On the ground, we have two curves that intersect. They're parabolas. You know, it might be better if I bring it like this first. Okay? So if we're looking straight down at some solid right now. And we're saying that the shadow of this solid on the ground is the intersection of these two curves. And then the solid is actually formed by creating rectangles above it. Right, so you cut it. Remember we said we come in, we cut it with a perpendicular like this, perpendicular but parallel to the y-axis. We cut it, and when we look at that from the side, it should be a rectangle. So now I'm going to turn it like this. And can you see, let's say right down the axis, if I go up and then straight over like this and down, I have a rectangle. But as I get closer and closer to the edge, those rectangles get smaller and smaller. Well, if you put them all together, right, all of them, infinitely many, you get a solid. And then that solid would look like this. Right? What's the volume of that solid? That's what we were asking last class. Now I can change it. Instead of doing rectangles, I can do squares. So now the length of the length, let me see if I can zoom in on this. I forget what my zoom is. I think I've had problems zooming in here before. Oh no, that worked okay. So if I look at the distance, see along this edge right here, this line connecting those two, the red and the blue there, if whatever that length is, I go up the same length and over the same length and down the same length, that's a square. And then if I move further in, then the length across is longer, so my square is going to be bigger, right? I keep doing that all the way across and put them together, and I get that. Circles. Let me do semicircles. Semicircle would be just the top half, right? Top half. So I go across that edge again, I make a circle with diameter of this, right? Or you could say that the radius is halfway, and then you just swing it, all right? No, take that back. It's only halfway if it's symmetric. But the radius, the diameter of the circle would be the distance between those, the red and the blue. So if I come over here, same thing, same thing. I put those all together, I get that, right? It's hollow. That's because my code isn't perfect. And then if we do triangles, it would look like this. And circles will go all the way around. Okay? Oops. Now does that make a little more sense visually of what I was trying to explain last time? Let's see what their code looked like for that. Cross sections. I want to see their code. Their code's just more advanced than mine. It's because I have limitations in my knowledge of coding, all right? But I do my best with what I got. So so here's the ground, okay? And above that ground, they're making squares, right? So that's what it would look like. Oh, sorry, yeah. The base region is circle, and then top is square. Here's what equilateral triangles would look like. So, hey, I mean, theirs isn't that much better than mine, right? Come on. And then this is the circle, semicircles, and then rectangles, right? Then you can change it to a square on the bottom. You can change it to a triangle on the bottom. You can change it to just two functions, which is what I was doing. There's squares above. Hey, theirs is kind of hollow looking. I don't like theirs. Theirs sucks, man. No, I'm just kidding. You get the idea, though, right? This is actually pretty good because you can see the diameters and how they keep on getting bigger. So it gets a little bit higher as you go in. And then what's this last one? Undulating. So you've got the grounds doing that, and then above it you got circles. That's kind of cool. Okay. All right, so I hope that helps with the visualization of what it is that we're doing. I mean, when you look at this, I mean, you can really find the volume of pretty complicated looking things, can't you? I mean, but things that you might see in the real world too, right? Just trying to think of something in the real world that you would want the volume of. I don't know. A pot or something, or I don't know. The first thing that comes to mind right now, I don't know why, is like a piston. Because pistons are not perfect cylinders, right? There's different things going on. It might be hollowed out in the middle or something, right? So you could find the volume of that if you could somehow describe what each cross-section looks like. So, whatever. All right, well, that leads us on into what we're going to do today, which is we're going to move to 7.3. Not everyone on campus here covers 7.3, but I think we'll just briefly touch it so you know it exists and you know about it, and then we'll just move on, all right? So 7.3, we're going to do volumes again. Same thing we were doing. So volumes of revolution again, where we're revolving things. So throw out that whole idea of cutting things perpendicular cross sections. That's just like an end note of 7.2. Let's get back to the idea of rotating things around the rotating things around some line. I'd like for us to motivate today, and I've got to still fill in one more thing up here, but I don't want to give it away. All right. So let's start with this example. Let's say that I wanted you to rotate the following. Let me tell you what it is, and then we'll draw it. Y equals 2x, what is it, squared minus x cubed. Okay, so I want to take the region that's bounded by the region bounded by this and y equals 0 in the first quadrant in Q1. First quadrant, y'all understand what I mean, right? Okay. So we need to be able to draw this. So given enough time, we would draw it, right? We graph it. And since I've got the internet open and I've got Wolfram Alpha right here, I'm just going to graph it for us real quick. It was 2x squared minus x cubed. There it is. Oh, look at that. Perfect. It's in the first, this is the first quadrant right here, isn't it? That's the picture of it. So I'm going to go back here. It does something like this. It comes in here, it goes up, and it comes back down. Now, I would need to algebraically be able to figure out where these 2 points were, which you could do by setting this equal to 0. So I'll find that real quick. When does 2x squared minus x cubed equal 0? Just factor out x squared. You're left with 2 minus x equals 0. And then the only two solutions to this are 0 and 2. You follow? Okay. All right. So this should be everything we need. I would like to rotate this. Okay. I want to rotate this. I haven't told you, right? I didn't tell you where I want you to rotate it. I want you to rotate this about the y-axis. Tell me what you think about that. What? Why? If you can. What's that? This is our region, right? I want it to go about the y-axis, not the x-axis, right? So I don't want it to come this way. Yeah, I want it to go this way. There's going to be a gap in the middle, right? But how are you going to do it? Well, the only thing we know how to do right now is if we're going to go this way, we draw a rectangle the other direction, right? Like this. What is wrong with our rectangle? The outer function is the exact same as the inner function, right? The inside and outside radius, right, of our rotation is actually the same function. So you can't subtract the same function from itself. You'll get 0. It won't make any sense. And that's because that blue thing is not a function of y, right? It fails the vertical line test. Well, turn yourself over. It fails that test if you try and draw a line this way. It hits the graph 2 places, so it cannot be a function of y. Understand? There's no way around it, okay? With what we've learned up to this point, you can't do this problem, which is why I feel like I need to show 7.3, because if you just see 7.2, you get to this, you're stuck. All right? So what we need is a way of handling this, right? But what we need is for our rectangle to be vertical, because if it was vertical, we'd be able to do it, wouldn't we? Like if it's vertical, it's okay. I can define the top and bottom pretty easily. Agreed? All right. So this is a problem. We have an issue here. So I'm going to put under here. We have issues, big time issues that have nothing to do with calculus, right? We need to figure this out. So let me see if I can convince you of another approach to finding a volume, if that's going to go around the y-axis, right? See if you believe this. Let's say I take my rectangle, right, and draw it right here. Well, I won't use blue. Let's say I take this green rectangle in here. If I were to take that green rectangle and rotate it around the y-axis, okay, around the y-axis, it would look like this. Would it be solid? No, it would be hollow in the middle, wouldn't it? Looks something like that. Now my y-axis would be right down the center like this. That's what that one rectangle rotated around the y-axis would look like. We all in favor of that? Now, try and remember what we did when we came up with the formula pi integral f squared minus g squared, which was this right here. Remember what we did when we came up with this formula? We said if we're going to rotate this around, when we rotate around, we get this washer, and we went off trying to find the volume of that washer. We tried to come up with a formula for the volume of that washer, right? And the volume came out pretty naturally because we knew the volume of a cylinder, right? A solid cylinder. So what I'd like to do is see if I can convince you what the volume of this is, all right? So here's how I'm going to do it. I'm going to come in here with my imaginary pair of scissors, and I'm going to cut this thing, right? And I'm going to lay it down and roll it out and lay it down on the floor, okay? If I do that, it'll look like this. Won't it? And now that's a box, basically. A three-dimensional box. It's not a box, not all sides are equal. We call this, anyone know what we call this? Have I mentioned that to you? It's the technical name is parallel piped. Parallel piped. That's a three-dimensional rectangle, basically. So we'll just call it like a rectangular box, and I think everyone's, it's a shoe box, man. It's a weird shoe box. All right, so we've got this parallel piped. The volume of a rectangular box or parallel piped is length times width times height, isn't it? Length times width times height. So I know that the volume of this one thing will be, I'm just going to say length times width times height. So we need to come up with what each of these are. Let's start with the width, and I mean width being this little width right here. How wide is this thing? Yeah, it's dx, isn't it? Isn't the width came from rotating that around, right? So the width is like that distance from here to here, and that's dx. So this side right here is dx. How tall is this rectangle? What's the height of it? It's, in this case, it's the function on top minus the function on the bottom. Same thing we had before. Now, in this particular case, the bottom function is what? 0. But if it were not 0 and raised up, it would just be the top minus the bottom, wouldn't it? So f minus g, not squared or anything, just f minus g. You all agree? So I'm going to say this side is the top minus the bottom. We mean my picture that goes with that. Here's my rectangle. We have a top function. We have some bottom function. And now for the big one. What is the length of this? It's the trickiest part of the whole problem. It's the circumference of the circle, right? If I get a circle, right, and this is what we had to start with. Now it has some thickness to it, right? But when I cut it open and I laid it out, the length here is the circumference of the circle. So I need the circumference of this circle. We have to be extremely careful here, though, because our circle was created by taking this and rotating it around the y-axis, right? So the radius of this circle is actually the distance from here to the rectangle. So remember when we integrate with respect to x, we have two limits of integration, right? A and b. And so what happens is we start at A and we move across to B, don't we? And we have an infinite number of rectangles in there, but when we move from A to B, what is it that's moving? What variable is actually changing? X, right? It's the value of x is going from A to B. So this distance from the origin to that rectangle is the variable x, isn't it? It's x as it moves. So I'm going to label this distance right here, from here to here, x in this particular problem. And x in our problem starts where? X for us would start at 0 and then end at 2. So if that's the radius of this circle, right, in my picture, in this picture, that would be the distance from here to here. Now, are you concerned that there's a thickness in that, x, which one is it, the inside or outside radius? Are you worried about that? Are you thinking about that? Why does it not matter? There's going to be infinitely many rectangles, right? Which means the width of the rectangle is going to go to what? The width of the rectangle is going to, as we put more rectangles in, the width gets what? Smaller and smaller and converges. So the distance of x, yes, there is a difference between the outer and inner, but as you let these go to infinity, this basically pinches it down to only one number, so x can only be one thing. Does that make sense? This is the beauty of the limit. The limit is what allows you to do this. It's the fact that when you take the limit, everything squashes down to basically a single point or a single line. But we can come up with the geometry of it this way. All right, so what is the circumference of a circle? Two pi times the radius. 2 pi times the radius, or pi times the diameter. So this is going to be 2 pi times my radius, but what's my radius? X. So the volume of that one particular piece right here will be all three of these multiplied, right? It'll be the 2 pi x times the top minus the bottom times dx. 2 pi x times the top minus the bottom times dx. That's the volume of that one slab. How do I get all of them? Integrate, right? Integrate from a to b. What can come out of the integral? The 2 pi, right? The x has to stay because we're integrating with respect to x, so it's a variable has to stay in the integral. So the volume total, volume sub t, is going to be 2 pi, the integral a to b, bless you, x times top minus bottom, bottom dx. If you want, we could label the top one f and the bottom one g, and then this would be f minus g, right? If it makes you happy to do it that way. This is great. Yes. Good question. Very good question. Well, what is it that we're letting vary in this problem? What's changing? X, right? So a and b will be our restrictions on that variable, x. So it will go from 0 to 2. We will not look this, we are not looking this way. All right? What I'll do here for this formula, I'm going to go to the next page. Well, I think we have enough because of what we did in 7.1, now 7.2, and now this. I think I can go straight to an example. Let's just go back to that problem now and answer it, right? Because we were stuck. So for our particular problem, we had this situation. This was 2x squared minus x cubed, right? And then that's our top function. Our bottom function is what? Y equals 0. Right? Y equals 0, the bottom. So really, it's like it's not even there. So the volume, if I rotate this around the y-axis, notice I'm drawing my little axis of rotation here. The volume will be 2 pi integral 0 to 2 of x. Then the top function, 2x squared minus x cubed, minus the bottom function, which is nothing, dx. And that's just a power function. Distribute the x through, and you're there. Uh-huh. Sure. You sure? Oh, okay. Okay, so we're all right then? So we usually employ this method when the other method doesn't work, when we can't use it. We pull this one out. I personally like this method, just period. I just like it. So like any time that I can rotate using this method, I'll use it. Mostly because you don't have to square anything, right? Now you will have an x out here that you have to distribute, which might mess things up, but um, you know, is what it is. So if we go back to last class, I don't want to make things too crazy here, but if I go back to last class, and let me look at how much of this could we have done with shell. I told you what the method's called, sorry. I'll tell you. Okay, so how about this one? You know what? No, that's... Let me get back to the beginning. There it was. Okay, so let's take this. I gave you this region, right? First thing I said is rotate it about the x-axis. We would just use the method that we normally had, which was the washer method, right? No problems there. We have a top, we have a bottom. So pi, the f squared minus g squared. Now, if we want to rotate it around y equals -3 this way, right? Stick with washers still, right? Stick with washers. Y equals 4, same thing, right? But what about if I would have given you this problem and I say rotate it around the y-axis? What would you have had to have done? You would have had to rewrite this instead of y equals x squared. You would have had to rewritten it as x equals whatever, a function of y. You would have had to solve that one, x is a function of y. Then you would have done parametric plot on your calculator, maybe, I don't know, and you would have tried to visualize everything again, right? And then your integral would be with respect to y. And your rectangle would be horizontal instead of vertical. But can you use the method that I just showed you? Yes, right? This integral, if I set around the y-axis, would be what? 2 pi integral where to where? This was 0 and 1, okay? It was 0 to 1. Then what's the distance from this axis of rotation to my rectangle? Well, that's your x value. And then the top minus the bottom. So which one is on top? Square root of x is on top, and then on the bottom, x squared dx. And you're there. You're done. Okay? Without switching anything. Now, not everything will work that way, but you know, if it's there, you can use it. So on your test, if I ask you to find a volume of rotating something, and you want to use this method, you're free to, as long as the problem lends itself to that. One thing that I've told students in the past is, like, if you're confused on the method, if your rectangle is perpendicular to your axis of rotation. See, this rectangle is perpendicular to this axis. You're going to be using washers, f squared minus g squared. If your rectangle is parallel to your axis of rotation, you're using the other method, which is called the method of shells, cylindrical shells. All right, so now I'm going to go back to my note for today, day 14, go to the top, and I said, what is today about? Here we go. Right here, volumes of revolution. This section is, I'll say exactly what it says it is. I think it's just shells. Oh, cylindrical shells. Most people who have used this method, shown students methods, other people you meet that have done Cal 2, they'll just say, yeah, I use shells for that. Okay, I'd like to give you a problem that's going to be a little more challenging, but let's see if we can handle it or not. So how about rotate region bounded by y equals we'll stick to some simple stuff. About x equals -2. What I like to do on a test when it comes to these problems, what I like to do is I like to give you I like to say, here's a region, okay? It's bounded by these curves. Boom, here's the region. Go figure out what the region looks like. Now, find its area. Now, rotate it around the x-axis, find that volume. Now, rotate it around the y-axis, find its volume. Now, rotate it around y equals 2, find the volume. Rotate it around y equals -4, what's the volume? Rotate it around x equals, and I give you like, you have the area, then you have a rotation around x, rotation around some line, other line, up and down maybe, and then rotation around y, and then move those lines. So you basically have one region that you rotate like 5 or 6 different ways. But it's all just the setup, right? Just as long as you can set up the integrals, you're done. All right, so we've discussed this region. We did it last class, and that's the one I just showed you right now. Goes like this, and the other one goes like this. That's pretty good. The one on top is y equals the square root of x. The one on the bottom is y equals x squared. I want to take the region bounded by those two. I want to rotate it around where? X is -2, which is a vertical line, isn't it? Now this is not drawn to scale, but there's -2. And here's your axis of rotation. All right, so when you're doing this, you look at it and you say, all right, could you use washers? Could you use washers? Your rectangle would be horizontal, right? And then you would have an outer radius and an inner radius, right? The outer radius would be controlled by the blue function. The inner radius would be controlled by the red one. And that means you would have, since you're sideways like that, you would have to do both of these solve for x, right? In terms of y. So it could be done with washers, couldn't it? But could we also do it with cylindrical shells? Yes. And that way we get to leave our rectangle vertical like this, right? And then we're going to wrap it around this way. Now, you know how in the other problems I like to draw a separate picture that show my axis of rotation and everything? I'm going to do the same thing here. I hope you will appreciate why in a second. I'll do it right below. Here's my y-axis. Ooh. Here's my rectangle. Here's my top. Here's my bottom. That's the thing that's going to get wrapped around this dotted line, right? The top and the bottom are pretty clear, aren't they? Yes? The top function is square root of x. The bottom function is x squared. So in the formula, it was 2 pi integral x top minus bottom dx, right? But be careful, because in the formula I gave you, x was really representative of the radius, wasn't it? The radius of the shell. And in the picture we had, it was x, because it was from the origin to our rectangle. Here, yeah, here our radius is actually the distance from here to here, or from here to here. And we know that this distance right here is 2, and we know the distance from the origin to our rectangle is x. So our true radius isn't x, it's actually x plus 2. So in the formula 2 pi r, the r is this radius x plus 2. Any questions? Do y'all understand where I'm coming from here? Okay? So this will become 2 pi, that still stays the same, integral 0 to 1, now the radius of the shell, which is x plus 2 or 2 plus x, doesn't matter. And then top minus dx. There you go. And you could FOIL that out, get power functions, and then integrate term by term and be done. So that's my opinion also. That's my opinion also, but you know, this is the only thing that really gets adjusted, is that radius rotation, yeah. they just would not be presented with a problem that they, like the problem I showed you before this, you can't do the other way. Like this one cannot be done with washers. You cannot, because you can never get this, well, I suppose you could somehow try and break this function at its max point and come up with a function of this and then a function of this. You could probably do it, but the algebra of that would be a tremendous effort. So yeah, I don't know. So they're just not covering that, and that's an opinion of different instructors. We all have our different opinions on things, you know. So yes, yeah, yes, that doesn't change. Yeah, and think about it, because this is what's really cool about this formula. When x is 0, what's your radius? 2, right? When x is 1, what's your radius? 3. And you can kind of tell from the picture that when x was 0, right, this radius is 2. And when x is 1, that radius is 3. And anything in between, that rectangle will be, yes? Oh, that's what we're about to do. Yeah, that's the next example. So let's do the exact same problem. Let's rotate it around. Let's get something on the other side. So how about x is equal to 5? Same problem, rotate around, about x is 5. So come in, draw my picture. Trying to stay consistent with my colors, and every time I do it, I do the opposite. Damn it. Okay, the blue and the red. Okay, I want that region. I want it about x is 5. Root x on top, x squared on the bottom. Could we do washers? Yes, we could. We could go horizontal, rectangle. We could wrap around. We might have some issues, but you've got your note cards, so that would be no problem, right? This would be almost exactly like the note card you showed me. So we could do it that way. But the shells will be so much cleaner because we have a top function, bottom function. We've got our axis of rotation, right? So remember what I said. A way to confirm that shells is going to work is if your rectangle has a top and bottom that are different, which it is, and then the axis of rotation we're trying to go around is parallel to that rectangle. If that's happening, you have to use shells. So really the only thing to actually determine is the radius, right? That's the real work of the shell method, is determining that radius. So what is the radius? Isn't it it's the distance? Well, I said I would like to draw my other picture, so go here. And then here's my y-axis. My rectangle is inside here, right between those two. And I know that the distance from the origin to here is x, right? That's x. But the radius I'm talking about goes from there to here, right? From here to here. So what is that distance? 5 minus x. Because the entire distance is 5, right? So this will be 5 minus x from here to here. And that is our radius. I'm just going to label it r for radius. Does it make sense that that would work? Well, what are our limits of integration? 0 and 1. If x is 0, what's your radius? If x is 0, what's your radius? 5. Is that right? If x is 1, what's your radius? 4. X is 1. Is that distance 4? Yeah, because remember that's 1. So anything in between should be all the rectangles in between there. So the formula, the integral, the volume is 2 pi, 0 to 1, 5 minus x. root x minus x squared dx. Because we're using shells. That's right. I don't know. If you ask me, and I think you've already alluded to this, I mean, this just seems so much cleaner than doing it the other way. Now, don't get too excited, because not every integral can be done with shells, right? Just like not every integral can be done with washers. So sometimes you're forced to use one way or the other. So on the tests, the regions I give you will go by, usually if I'm going to ask you a bunch of different questions, it'll go by washers in one direction only. And so you can't use shells in that direction. And then the other direction goes, you can do either way. So it's up to you. And if you use shells, then, you know, I actually like that, because it means that this made more sense and it was worth us doing 7.3. So, uh-huh. I'd like everyone to get into the habit of the drawings and labeling of things. Because if you just give me an integral, like what if you just give me this integral and you put here x minus 5? How much do I take off for that? It's going to be wrong, right? I mean, it's off by a sign. But I mean, that's the sort of thing where if you just give me the integral and there's no picture to go with it, then I have to take off more than I would if the picture's all good. You just kind of, oops, flip that around. So just show as much as you can. The drawings are a good thing. And especially with, if you do take Cal 3, I mean, you know, things that are happening in Cal 3 are three-dimensional. So what you have is, you have this on the ground, right? You have something like this on the ground. And then above this, like a surface, you have something else happening. Do you want to see it or not? We don't have to get into this. I'm trying to answer your question is, you know, what should you show? Oh, here, I'm bringing up the wrong thing. Chapter 11, no, chapter 11, see, no, chapter 12. Almost. All right, well, you know, I can show you that. That's probably good enough. But you can almost see that what we have right here is what we're talking about right now, right? An area between two curves. And so imagine, come on. So imagine you have a region on the ground, right? I could ask you for the area of that, right? Yes. But let's imagine above it you have a surface, okay? And you just allow these things, like if you're on the ground, you're standing on the ground, you look up into the surface and you see where that thing on the ground goes into the surface. Do you see that? That would be like the image of that shape on the ground up into the surface. And then you find the volume of the solid below that. Do you see that? Okay, so all of that is going to involve, like on a test, or when you're trying to do these problems, the first step is to set up the region and draw the region. And then, so the work involved, again, it's just going to turn out to be an integral, right? It's just going to be, this one will be what we call it's a triple integral, double integral. So in the work that you do, it's drawing. It's a lot of drawing. So I would advise you at this stage to get very comfortable with the drawing, because it'll help you later, you know, be comfortable with that sort of thing. I hope that addresses your question. Okay. Yeah, here's a general picture of what's happening. These are really cool, but take Cal 3, you'll see. Where are we? All right, that's pretty much it. I mean, I wouldn't go, I'm not going to go crazy and put like the region on the other side over here and try and confuse you. Do you have any idea what would happen, though? Maybe I am going to confuse you. What would happen? Okay, so like let's say you would have had a region that was like this instead over here, and I want to rotate that around here. Let's say this was like -1 over here and 0. There's your rectangle. So what's your radius going to be? So where is x this time? It's over here, right? So do I call it x or do I call it -x or what do I call it? Let's stick with x for now, okay? And let's just remember, because I'm on the left side of the y-axis, whatever this is negative, right? So what is the distance between here and here? Oh, I didn't tell you what this line was. Well, how about 2? Okay, let's say that that's 2. Then this would be what? 2 here, and then it would be like an absolute value almost, but let's not use absolute value because we don't want to put that in the integral. Think about it. If x was -1, right? If x was -1, what would you need that to be? What would you need your radius to be? 3, right? So I cannot say that this distance right here is 2 plus x. Because if I plug -1 into this, what do I get? I get 1. I need it to be 3 when I'm at -1, right? And then when I'm at 0, I need it to be 2, right? Now that worked. But I would need to change this to what? Say again? 2 minus x. Because now when you plug -1 into this, you get +3. And when you plug 0 into it, you get 2. You plug -1/2 into it, you would be at what? 2.5, which would be that distance. So I'm not going to do that to you, but we ran into this last class, didn't we? We had to say, oh, but wait, that's a distance, so we have to take the opposite. That same sort of thing can happen with shells. But I'm going to stick everything in the first quadrant and make sure everything's good. Yes? Cosine x? Like that? Oh, yeah. Cosine, same thing though, right? God. So, what's your question? What? Yeah, you would have to break it up into 2. You would have to do this one first, where cosine is on top and what's on the bottom? 0, right? And then when you go here, you'd have to have these rectangles where what's on top? 0, and then you're subtracting what? Cosine. Yep, you could do shell on that. All right, I think that's it for 7.3. Yes. Yes. That's right. Yeah, and something's wrong there. There's a way you can generalize that formula if it really, well, no, I won't do it. I don't want to make things worse. Page 385 for the homework off this, page 385. Probably 15 through 25, the odds. Now on 21 through 25, or 22, 21, 23, and 25, on those, it says to set up the integral, and then it says use a calculator to find the value of the integral. I would say on all of these, same thing that I said on the last homework. Just set them up, all right? Set them up. What I've done in the past is I've given the, like on your test, see, it won't happen here because we don't, do we have another? No, we do have another test. I take that back. I was thinking you only had a midterm and final. Is that on the next test, you set up all the integrals, right? Set them all up, set them all. That's what you turn in for the test. Then you take home those integrals, like you take home the test, a copy of it, and you actually evaluate those and turn those in next time we meet. So like 90% of the grade is the integral setup, and then the 10% is what you turn in after you go home and figure them all out. But, I mean, I don't know. That's kind of like a thing. Do you want that or not? You know, like for me, you set them up, I'm happy. Do you want to go and get that 10 points based on you computing, or does that seem like tedious work to you? You know? We'll talk about it more. We don't have to decide right now, but what's your feeling just initially? Too tedious? Yeah. Bonus? Yeah, but that's a lot for me to have to grade too. Yeah, I don't know. I wouldn't want to go through all of those integrals with all the little power things and make sure that you integrated, you know, x to the 3/2 properly, and oh, find your little error, you know. Scantron, is that what it? All right, so we're done with 7.3, which brings us into 7.4, and we still got 20 minutes, so I can at least talk about this. All right, as I try and set this up, let's just think a little bit about, and we're going to back up a little bit and just think about curves for a second. We are talking about arc length right now. So arc length, imagine that you have a curve, starts at one point, ends at some other point. And close Mathematica, it's trying to do a bunch of stuff in the background there. So we have some curve, right? And let's say that this curve is given by y equals some function of x. So it passes the vertical line test. Now, if I take, try and do this. If I take that curve, right, there it is, right, and I take it off the page, right, and I straighten it out and I lay it down and I measure it, that would be the length of that curve, right, which we call the arc length, right? So that's what we're trying to figure out. We can't use areas because we're not even talking about areas, right? So hopefully one of the things you've picked up in this class is the power of calculus is that we try and come up with a formula that represents the length of a little piece, and then we make them infinitesimally small, right? And we add them up, right? That's basically what the integral allows us to do. So what we'd like to do is kind of zoom in on this and take a look at what the length of a tiny little piece would look like. Yes? And then come up with a formula for that, and then add them up. So let's try and come up with that formula. So going back to curves, if I were to have a curve, I'm going to zoom in a little bit here. If I had a curve that did this, and I'm just going to look, so we're kind of blowing up a little section in here, right? You've seen this sort of view before where we blow up that little zoom in on that little piece. I don't want that circle out there. Then if I construct a right triangle like this, now I've gone like really small, right? Just like when we were doing the area under the curve, I drew a rectangle and I said it's going to be really small, the width. I've gone in here in a very, very narrow window. So if I do that, then the width of this I could call what? the width of this little infinitesimally small piece, dx, right? I mean, that's my change in x, right? If I want to get from this point to this point, I have a change in x and I have a change in y. Maybe that'll help. Right? This is change in x. This is change in y. I'm using the delta for change. Change in x, change in y. But on the infinitesimal scale, when we go and let that change go to 0, that's where the dx comes from. So we have basically dx on this side. And on this side, we actually have the infinitesimal change in y with respect to x. So whatever x changes by, this would be approximately dy. Yay or nay? With respect to x. So, is that okay like that? So, we think about a function. If I change x, the y changes, right? But how much the y changes depends on the actual function, right? If it's x squared, it'll go up pretty quick. If it's x to the 10th power, it'll go up really quick, right? Well, as long as I'm past 1. Remember we talked about that? Okay. So, all right. So so the dy dx is dependent upon the function itself. So this value varies. Now, do you agree that that length of the blue? I think the length of that black arc is approximately the length of that. Approximately. And how would I get a better estimate? If I make this smaller, right, doesn't that error become less? I'm not going to go and draw these, but if I make my rectangle here instead, right, then draw my line like that, then it's a smaller error. And if I go even closer, right, then draw it, it's even smaller and smaller and smaller. Well, that's what dx means, doesn't it? Dx means we're going to let it go basically to 0. We're going to let this thing go to 0. So that green line is going to be approaching the true length of that black arc. And what is the length of that green line? It's dx squared plus dy dx squared, but then square root. That's the length of that little piece, isn't it? What do y'all think? Is this a formula? Can you see a formula in here? We need to add all those up forever, right? But if you do it this way, then dx is trapped in there. Wouldn't you agree? You wouldn't want to integrate something with the dx underneath a root, would you? What is the derivative of x with respect to x? What is dx dx? It's 1, right? Isn't dx, so when I say how much is x changing with respect to itself? It's always 1, right? So if I change this by 1/1,000,000th, x will change by 1/1,000,000th. So the ratio of the change is always going to be 1. So this becomes 1 squared, which is 1. And what is dy dx? That's the derivative, isn't it? I mean, that's the derivative of the original function. That's y prime if you want, and then squared. Dy dx is the derivative of the original. It's like the slope of the tangent line, right? Slope of the tangent line is basically going to give us that infinitesimal change in y. So the integral, if we add them up forever, the total length, so I'll say length t for total, is going to be the integral. Now x is going to vary from a to b of the square root plus, of square root of 1 plus y prime squared. And then we have to have with respect to a variable. So obviously, hopefully, obviously to you, dx is our integration variable. Now this is a very loose way of explaining where it comes from. Do you buy it though? There's other approaches to it, but I think the triangle is like the easiest way to do it. That's the formula. I mean, there's nothing more. So all this section is really about is applying the formula. Okay, we'll do a. I don't know if this is going to work out. We might run into a problem, but let's see what happens. Oh yeah, I know we're going to run into a problem. I remember I tried this once. It didn't work. I better stick. These problems, you've got to pick them real special or else they'll fall apart. How about we try and find the length. Find the length of y equals x to the 4th over 8 plus 1 over 4 x squared on the interval 1, 2. All right, so all there is really just a formula to apply here. That's it. We don't have to draw. We just go to straight to the formula. So the length of this should be the integral 1 to 2 of the square root of 1 plus, and then the derivative of y squared. So since you're going to need that, I always recommend you go find the derivative of y over here first. The derivative, not the antiderivative. What is the derivative of this right here? 4/8, so 1/2 x cubed. And then what's the derivative of this? So maybe move the x squared up as an x to the negative 2 and then take the derivative. So negative 2 comes out. So negative 1/2, is that right? X to the negative 3, careful there. That's my derivative. And what do you have to do with that derivative in the formula? Square it. So I recommend you do that over here also. So now, what is the derivative squared? Well, that means I'm going to take 1/2 x cubed minus 1/2 x to the negative 3 times itself, 1/2 x cubed minus 1/2 x to the negative 3, right? That's what I'm doing. And you could FOIL this out if you wanted to. That's what I'm going to do. Not the only way to do it, but I do this times this, which is 1/4 x to what power? 6. Okay, when I do this one times this one, I get minus 1/4 x to what power? 0, because 3 minus 3 is 0. So x to the 0 is 1. So that's just going to be negative 1/4. When I do the inner one, I get what? Minus 1/4 again. And then the last one plus 1/4 x to the negative 6. I'm going to clean this up just a little bit. I have 1/4 x to the 6th plus 1/4 x to the -6 minus 1/2. Is everyone still alive? Everyone good with this? This is the derivative squared. Now remember I said that we have to pick these functions very carefully for them to work. Believe it or not, when we plug that in, things are going to happen that are going to be good. It's going to take a little algebra to get to it, but 1/4 x to the 6th plus 1/4 x to the -6 minus 1/2. And then don't forget on the outside dx. Now that may not appear right now that anything good is going to come from that, but it will. So here we go. Does anyone have a question at all as to where I got any of that? Let's do the 1/2. The 1 right here minus the 1/2 is 1/2. And then I'm going to rewrite this way. X to the 6th over 4 plus 1/4x to the 6th. And that was it, right? Because I took that 1/2 out of there already, that negative 1/2. And you look at that integral and you start thinking, whoa, wait, hold on. I thought all my techniques of integration, like this is, I've never seen anything like that. And I agree, we really never did. But you have 3 terms, right? And you can combine all those terms together if you get a common denominator. So what would a common denominator between those be? 4x to the 6th, right? So let's do that. I'm going to have to multiply the first one here by what on top and bottom? 2x to the 6th on top and bottom. So I get 2x to the 6th up there. What do I have to multiply this one by, top and bottom? X to the 6th. So x to the 6th on top times x to the 6th is x to the 12th. And then on the last one, do I have to put anything? No, so I have plus 1. That's all over the common denominator, which is 4x to the 6th dx. Integral 1 to 2. Sorry, I forgot that. Any questions there? A little more work. Like I just said, they have to pick these very special so they work. So you should know that when you're doing this for your homework or whatever, or on test, that things will simplify algebraically if you just massage it enough. Yeah, hang in there, exactly. Anybody recognize the numerator? How many terms in the numerator? How many terms? It's like a quadratic type, isn't it? It almost looks like x squared plus 2x plus 1, which does factor. But this one isn't going to be x squared plus 2x plus 1. This is x to 12th. So isn't that x to the 6th plus 1 times the same thing? You have to be able to see that though, right? This factors to this. And then isn't that, since it's the same thing, that may as well be x to the 6th plus 1 squared, right? On the top, I have x to the 6th plus 1, but then squared. And on the bottom, I have 4x to the 6th. And so if I have a fraction and I have a root, I can do the root on the top and the bottom, and these are both perfect squares. When you take the square root of the top, what are you left with? X to the 6th plus 1. And on the bottom, you're left with 2x cubed. Now we're talking. Because this right here can just be split up into 2 fractions, couldn't it? X to the 6th over this, 1 over this. And those are both powers of x. And now it's a pretty clean integration. What's x to the 6th over 2x cubed? That's, can I put 1/2 x cubed? And then 1 over 2x cubed would be plus half x to the, I'm going to prepare it for power rule, so I'm going to bring that up. That's it. At that point, dot, dot, dot. We're out of time. So maybe you can take a look at 7.4 if you want to get started on these. Okay, there's nothing else. I mean, the only thing I could show you in 7.4 is some of the algebra that you're going to run into. That would be maybe something that would be a little complicated. But as far as application of the formula, it's pretty simple. You find the derivative, you square it, you plug it in, you simplify, and hopefully the integral is good. I mean, there's nothing more. So on this particular section for homework, you could look at page 391, and you could do 7 through, well, let me see here. I have some things marked. You could do like 7 through 17 odd. On your exam, which is coming up on what, Tuesday, right? Is it Tuesday? No. It's like the Tuesday after this upcoming Tuesday, right? On that test, for like arc length, you'll have just like one problem for arc length because the algebra in it's kind of ugly. The only way to get good at, get comfortable is just to go do those problems and get used to it. Boy, where are we? We did a lot today. That leaves us all of next week to talk about applications. So let's plan on Tuesday doing applications. So we're going to talk about like how you can find mass and center of mass and moments of inertia. And all it is just setting up the integral again. Just set the integral up. And that will leave us Thursday to talk about the test, practice some problems, whatever. All right. So I think we're good as far as time. I would just ask you to do your best to get caught up on your homework. All right. So that way next week, any review I do will be productive for you.